Here's an absolutely beautiful geometry problem. And today, I'm going to show you not just one solution, but two completely different ways to solve it. We have a quadrilateral ABCD. Notice that angle A and angle C are both right angles. Along the top side, CD, there is a point P. We are told that CP is 4 units and PD is 1 unit. We are also given a very important condition. The bottom side, AB, is exactly equal to the segment BP. And our goal is to find the length of the left side, AD. Let's call that unknown length X. Method 1, pure algebra. Draw the diagonal BD. This single line splits the figure into two right triangles, triangle ABD and triangle BCD. Since both triangles share the same hypotenuse, BD, the Pythagorean theorem will allow us to connect them. For triangle ABD, AB squared plus AD squared equals BD squared. For triangle BCD, BC squared plus CD squared equals BD squared. Since both expressions equal BD squared, they must be equal to each other. So we can write AB squared plus AD squared equals BC squared plus CD squared. Now let's focus on the smaller right triangle, BCP. Applying the Pythagorean theorem again gives BP squared equals BC squared plus CP squared. But remember the condition from the problem. AB equals BP. Therefore, AB squared equals BC squared plus CP squared. Now substitute that expression into our earlier equation. Replacing AB squared gives BC squared plus CP squared plus AD squared equals BC squared plus CD squared. And now the magic happens. The BC squared terms appear on both sides. They cancel immediately, leaving us with CP squared plus AD squared equals CD squared. Now plug in the actual numbers. CP is 4, CD is 4 plus 1, which is 5, and AD is X. So we get 4 squared plus X squared equals 5 squared. 16 plus X squared equals 25. Subtract 16 from both sides, X squared equals 9. And taking the positive square root gives X equals 3. So the answer is 3. But now let's look at a much more elegant geometric solution. Method 2, the geometry shortcut. Extend the segment DC beyond point C to a new point Q. Choose Q so that CQ is also 4 units long. Then connect Q to B. Notice what we've created. Triangle BCQ is a mirror image of triangle BCP. That means BQ equals BP. And since the problem tells us that BP equals AB, we now have AB equals BP equals BQ. In other words, points A, P, and Q are all the same distance from point B. That means A, P, and Q lie on a circle centered at B. Let's imagine that circle. Now look carefully at point A. Because angle DAB is 90 degrees, the line AD is perpendicular to the radius AB. And whenever a line is perpendicular to a radius at the point of contact, it is a tangent. So AD is a tangent to the circle. Meanwhile, the line DQ passes through the circle at 2 points, P and Q. That makes DQ a secant. Perfect. Now we can use the Tangent-Secant Theorem. The theorem says tangent squared equals external secant multiplied by the entire secant. Applying it here gives AD squared equals DP multiplied by DQ. Let's substitute the lengths. DP equals 1 and DQ equals 1 plus 4 plus 4, which equals 9. Therefore, x squared equals 1 times 9. So, x squared equals 9. And once again, x equals 3. Exactly the same answer. Personally, I love the second solution. Let me know which method you preferred, and I'll see you in the next puzzle.